Hello and welcome. In this video, we're going to look at the difference between series, parallel, and series parallel resistors. So this is a basic circuit, and if we hit play on this here, we'll see that the voltage across this single resistor is all of it, right? Whatever voltage we give this resistor, it will consume. So 0 on the bottom, 5 volts on top. And we see that that generates a specific current through this resistor, 50 milliamps for this specific combo right here, 5 volts and 100 ohms. You should be able to calculate that out at 50 milliamps. We divide those two. So if we stop the circuit, we can add another resistor here and see that we get a voltage division in series. We add in the second one and we hit play again. We'll see that the voltage comes up here, starts at 5 volts. And then as we trace down through here, we start to lose voltage. 2.5, that's half, right? And down at the bottom here, we're at 0. And so that is what we expected there. We expect it to have a voltage drop as we move through our circuit. We can also see that our current does not change. The total current changed, right? It went down because we added more resistance. But now it's about half of what it was before, and it's the same through both of those two components. So if R1 was a lamp or a light of some sort, then it's dimmer now because we added a second resistor in line with it and we slowed the current through that first one. So we can do that again, but put it in parallel. We can say that let's copy and paste this one out and put a parallel resistor in with R1. And that's going to allow us to kind of change some of the direction here. We'll hit play again. And here we see that the voltage division changed a little bit. We've got 5 here, 3.3 here, and 0 at the bottom still. So we expect the bottom to always be 0 all the way down to ground there. And that means that whole bottom section is all one unified location. Same with this top half here. So we expect 5 volts to stay up across to R1 and all the way down to R3. So we can leave those off to the side there as our potential. And then here we have our voltage drop in between. We know that the top half burned up half or a little under half of our potential that we had because we know R2 from right here from 3.3 volts down is going to be 0. So we know R2's voltage drop is 3.3. That's what R2 used, is 3.3 volts. So whatever else is remaining in that value would be what R1 used, right? R1 and R3. And we see that R1 and R3 both use that. Our current is different again, right? It's a little bit more this time because we got two pathways for current. We can travel through this one or through this one, which allows us to generate a little bit more, right? Then they come back together into this 3.3 milliamps as they travel through R2. That means that R2 is in series. So now we have R1 in parallel with R3 in series with R2. And we could put those together. We could put these two in the parallel equation and then add that to R2 and get this 3.33 total current out. So let's do one more. We can add another component in parallel with both of these. And this top parallel branch here can touch anywhere. It can touch up here, or it can touch down here where R3 is, and they would still all get the same voltage. Let's hit play on that. We see 5 volts across the top, and that just leads us all the way across. So that means that R4 gets 5 volts, R3 gets 5 volts, and R1 gets 5 volts, and R2 does not, right? R2 is the only one that has a voltage drop in its potential because it's going to burn up some voltage across these top two before the current comes back together. Right, so now we've got even more current. Our total current is increasing quite a bit. It's more than the first circuit, and it's more than any other circuit so far, right? 8.3. And that's because we have this open branch over here that gives us this 100 ohm drop. We have this 50 milliamps across R4. So R4 is fully loaded. It's got 5 volts, 50 milliamps, right? And as we trace down R3, we see that this one has 5 volts and 16.7 milliamps, right? And R1 has got 5 volts and 16.7 milliamps also. And we see that those two combine together to get us that 3.33 milliamps again, right? So that means that this first branch here is kind of independent of R4. R1, R2, and R3 did exactly the same thing it did when before it had R4 involved. And so this is very ideal. This is an ideal circumstance. In a real situation, you'd see that this voltage source does not stay perfectly at 5 volts. The more you add on, if we were to add yet another component, another pathway for our current to flow, then we would see that we have a little bit less voltage on our real battery, but this multi-sim circuit will not show that. Okay, so let's do a final evaluation of the circuit we just made here. So this circuit, if we trace up from the positive terminal here, we'll see that this whole top half here is all in parallel with something. That's our top node. And we know that that's all 5 volts. So after that, we can say that we have something in parallel. We have R1 in parallel with R3, and that comes back together to this node here. So we'll say it's R1 in parallel with R3, and that closes off, right? Because we started at a node, we ended at a node, and that means that these two are fully in parallel with only each other, and then something else happens. And so as we continue down, since we're not at ground yet, we can go through R2, and that's going to get us to our ground location, this bottom half here. So we'll say that that is in series with R2, and that gets us to ground. So now we're at the bottom of that parallel branch. We can go back up to our 5-volt top and follow a different pathway because we followed everything through there. So now we can go down and say we have a pathway through R4 that gets us to ground. And so that means that whatever just happened right here is in parallel with R4. We can do that one more time. We can say that we have another pathway through R5 in parallel to ground. And so we'll see that that is also in parallel with R5. Right, so watch out for this. You want to do innermost parenthesis first. So try to solve for R3 and R1 in parallel, add that to R2, and then you have a number, the combo of that, in parallel with R4, in parallel with R5. And you can plug all of that into one equation at that point and kind of really reduce it down. Okay, let us know if you have any other questions about how all this works. Thanks.